Hi there. In this video, I'm going to introduce to you an idea I call AH, altitude on hypotenuse. And so basically, here's the deal. What we do in this particular theorem is we start with a right triangle, and so that's necessary. Okay, you begin with a right triangle. Note the larger right triangle here. And we have a couple ideas to consider first. First of all, an altitude. Recall an altitude is an auxiliary line of a triangle that stems from a vertex and is perpendicular to the opposite side, or perhaps an extension of an opposite side. So this guy right here is called the altitude, and I'll just write ALT for altitude. And so for this particular situation, we say that this blue guy right here is the altitude on the original red hypotenuse of that right triangle. Okay, so we begin with a right triangle till we create an altitude to the hypotenuse. Okay, and of course, recall that the hypotenuse of a right triangle is the side across from the 90-degree angle. So if I were to ignore this, the red piece is the hypotenuse because it's across the largest 90-degree angle, or the largest angle, which is 90. And I'm going to create an altitude to that hypotenuse. Okay, and that's my altitude right there. Okay, what we have is we therefore create three similar triangles, and I'll show you that on the next page. Okay, and so what I'm going to do is I'm going to take this original starting point with my original blue, black, red right triangle, with the red piece being the hypotenuse, and I'm going to cut it up into three triangles. It's a large triangle, and I named each side. I'm going to name that blue piece leg 1, and I'm going to name the black piece leg 2. And the original hypotenuse I'm going to call the hypotenuse, the whole red piece. Okay, now that hypotenuse gets cut into two pieces, which I call piece 1, it's attached to leg 1, and piece 2, it's attached to leg 2. Okay, and basically what I did was I took the triangle 1 and 2, which make up the whole diagram, and I flipped them around and reoriented them so that they all have the same, they're all facing the same direction. Okay, and so if I take the whole triangle, right, so if I now kind of ignore this altitude here temporarily, that whole triangle is similar to triangle number 1 because they both share this particular angle right here. Let's go back to that altitude. Okay, so here's triangle number 1, altitude, piece red, black. I just kind of bumped it here. They both share that angle, the whole triangle and triangle number 1, and they both have a 90-degree angle. So they're similar by angle. I can say the same thing for the whole triangle and triangle number 2, which I bonked over here. So here's triangle number 2. They both contain this angle up here, the whole triangle and triangle number 2, and they both also have an angle. So by angle-angle similarity, all three are similar. So by the transitive property, since 1 and 2 are similar to the whole one, 1 and 2 are also similar to each other, if you buy that, which is true. So all three triangles are similar. Okay, so that said, what I'm going to do is I'm going to set up a couple proportions which give us the consequence of the AH theorem. Okay, the first one, I'm going to transfer the pieces over here. So I'm going to call this black piece leg 2, and I'm going to call this blue piece leg 1, which is what they are from the original right triangle. And of course that's my altitude here, here's my altitude here, and the red piece here is called piece 2 according to this piece right here. And this right here is, that corresponds with this piece here, I'll call that piece 1. Okay, so I just name the sides just for lack of better names. I call them legs and pieces and altitude. So one conclusion of AH is I'm going to take a look at the two smaller triangles, and I'm going to look at the ratio of the altitude. So if you can look at this altitude to piece 1, because they're similar, has to equal piece 2 to altitude. Okay, remember these two triangles are similar by angle, so therefore the corresponding sides have to be proportional. So altitude to piece 1 has to equal piece 2 to altitude. Now I'll write that out. I'll try to use my coloring. So altitude to piece 1 equals piece 2 to altitude. Okay, so again, to reiterate, left to left equals bottom to bottom. And that has to happen because the triangles are similar by angle. So the corresponding sides have to be proportional. Now if I multiply this out, what I get is the altitude by the means extremely meaningless, altitude squared equals the product of the two pieces. And that's one conclusion of the theorem that I call AH, altitude on hypotenuse. So what that means is the length of this altitude, this blue line that's perpendicular to the hypotenuse of the original right triangle, the square of that is equal to the product of the two pieces that it creates of the original hypotenuse. Okay? The other consequence of the AH theorem has to do with the legs. And now I'm just going to think about the original triangle and one of the two smaller triangles. And so let's just assume I'm going to deal with the big triangle and the medium-sized triangle number 1. Okay? And again, because they're both similar by angle, I can set up the following proportion. Right? So here's a leg here. That leg over this piece is going to be equal to the hypotenuse over that leg. Okay, so bottom to bottom equals top hypotenuse to this black hypotenuse. Okay, boom to boom equals boom to boom. So if I were to write that, leg 2 to piece 2 is equal to the hypotenuse, the whole red piece, the original hypotenuse of the original right triangle, over leg 2. Okay, so again, to reiterate, this, because these two triangles are similar by angle, okay, kind of ignore this altitude for now, then bottom to bottom, leg 2 to piece 2, has to equal red hypotenuse to black, leg 2, hypotenuse to leg. And so if I multiply that out using the extremely meaningless property, I get leg 2 squared equals the product of the piece 2 times the hypotenuse. Okay, and that's another outcome of AH. In fact, I can do the same thing if I were to choose the whole triangle and the small triangle. What I get in the same way is the leg 1 squared equals piece 1 times the hypotenuse. Okay, and that proof would be very similar to the one I just took you through, but instead of using the whole triangle and triangle 1 to get this particular, I would use the whole triangle in triangle 2 to get this particular outcome. So there are two general outcomes for AH, altitude and hypotenuse of a right triangle. Okay, and here they are to summarize. Okay, we begin with a right triangle. We bonk an altitude to the hypotenuse. Okay, I'm going to call that leg, is it 1 or 2? I guess it doesn't matter, but just to be consistent, I'll call that leg 2, leg 1, and I attach the piece 1 to leg 1. See how they intersect? And I attach the piece 2 to the leg 2. And of course that whole original is the hypotenuse of the original. And that guy right here is the altitude. Okay? The two general rules of AH are as follows, and they all come from triangle similarity. Number 1, the altitude squared, the square of the altitude, is equal to the product of the pieces. Okay? In other words, altitude squared is piece times piece. Well, what are we taking pieces of? Well, the only thing that's cut up into two pieces, the hypotenuse. Okay? So this particular altitude length squared is equal to that times that, as long as we have an original right triangle with an altitude around the hypotenuse. Okay, that's one outcome. Okay, the second outcome has to do with the legs. And to generalize that, the square of either of the legs is equal to the hypotenuse times the piece. Which piece? The piece that hits the leg. So for example, this leg squared is equal to the whole hypotenuse times this piece. Or the same thing can be said for the other legs squared. So the square of this particular leg is equal to the product of the whole hypotenuse times the piece that hits that leg. Okay? And those are our two general rules for AH, altitude on hypotenuse. Thanks for listening. We're going to use this tomorrow. I want you to understand where they come from, and the rules themselves aren't that bad to use. We'll take a look at those tomorrow. Bye-bye.